here. So for part 2, and of course these recordings are all available, and you should have them for all the way through, and even up to, I'll try to see if even the last semester's recordings are available for you all in case. Right, so this session now, we're going to review a little bit of signals and systems as it pertains to what we will be doing here. And of course, that must be bringing back very nice memories for you all of ECNG3025, right? But hopefully not all bad. Okay, so of course, let's look at a little bit of the vocabulary. Continuous signals, of course, are signals that exist for all time, right? So they like I have there, that's a particular steel pan note, right? This is its variation. The top figure is a variation in time. The bottom figure is a variation in frequency, right? So a continuous time signals, as we remember, meant that we had a value for the signal for all time. In theory, from time going t minus infinity to t plus infinity. But even when we look at the signal, all the values are defined all the time. And then if you take the time domain, right, if the signal is continuous, we can go to the time domain, and if you did the Fourier, if it's a periodic signal, right, remember, if it's periodic, you do the Fourier series. If it's non-periodic, you do the Fourier transform. Either way, you go from time to frequency, and the frequency of the signal is what we call the spectrum. So that this, and both of them give you the, one is like an X-ray into the other one. So the signal above, you know, it looks like it's varying in time, but it's not easy to say what that variation is. But then if you go from one domain, which is the time, from the time to the frequency domain, you're now able to see that that variation is in fact a 200 and something odd hertz signal that we're dealing with. In the case of discrete signals now, discrete signals exist only at certain values, at certain instances in time. Let me just zoom this up a little bit. Okay, so if you look at this, what we have here, this sequence is this set of numbers, set of values, right? So this is in fact not a discrete, this is a digital, right? This is digital because we've gone to a number here. So this is a digital signal, and look at its display here, right? So it starts, the sequence actually starts at n minus 4, 3, 2, 1, 0. So if you look at it here, this is really the n equal to 0 point, right? Whatever that n is, we don't know if that n is in time or if it is just a numerical sequence. But the fact is that x now has values only at these times. So there's a value at this point, there's a value at this point. There's nothing in between. And one of the big things to remember is that you cannot assume that because it is 1 here and it is 0.5 here and it's 0.5 here, that in between those two values or those two instances that the value is 0.5. It is a reasonable assumption, but you have to be very careful if you make that. You have to say what the assumption is, right? Now, that's the first thing. So it exists here, and of course, we remember from our signals and systems that we normally represent this by using square brackets. So we would call this xn, which is actually short for x n capital T. T being minus 4, minus 3, sorry, T being 1, n being -4, -3, -2, -1, and so on. Okay? And of course, we can delay the sequence. You remember in signals, we can delay something. So if I have xt, I could delay it by 2, which is x2 minus t, or t, sorry, xt minus 2, right? 2 minus t is to flip it around. So the one here now, if you look at the sequence above, right? The sequence above here has been delayed. And how much has it been delayed by? We delay it. Notice that we started at -4 here and we're starting at 0 in this one. So we have delayed this one. It's delayed because it has shifted in time later on. It is now delayed by 4 units. All right. So this is now x n minus 4. Yeah. In other words, the 0 time has gone. If I put n equal to 4 here, that's where the 0 time now is. It has gone from here to t equal to 4 here. Remember that? Yeah, no, maybe? Everybody all right with that? Okay. And here's an inverted sequence, right? So this is the same one. So this one is minus x n, okay? And then here now, the one at the bottom right hand of your screen is a discrete time unit step. So if you look at that, right, it's 0 all the way before t equal to 0, and then 1 all the points afterwards, right? Now these values occur. One of the important things again here is that these things occur at integer intervals in whatever, however we are sequencing. So we're going to have value at n equal to 1. We're going to have a value at n equal to 2. You're not going to have a value at n equal to a half. All right, so you must remember that these things here are integers, okay? Right, because we start counting from 0, we consider the 0, this is the first value. So n equal to 0 is 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, but this is actually the fifth value in this, the sequence. We are counting from 0, okay? And of course, well, this just explains the same, the values that we just had there, n minus 4 and so on. Right, and these things that we mentioned from before, that the convention is to right, that we use square brackets to indicate discrete signals. Of course, get in the habit of doing that, but sometimes even, like for instance, when I'm writing, I may inadvertently write something like this, okay, or x n t, okay? It's really supposed to be a square bracket, right? It really should be that. But what happens by putting n or nt, I know, or the reader will know that you're not dealing with the continuous time domain, which is would have had a lowercase t. All right. Some textbooks again may use the regular brackets and so on, but we will try to indicate that we will try to stick to our convention of using square brackets, and most because the square bracket also reminds you that it is an array of values. So xn could be 1, 2, 5, 9, minus 7, etc. Right? So it's like an array, a matrix. And of course, these are the manipulations and so on, the unit step. all things that we know. Right. So this is a discrete signals now, sinusoids, and I'm going to make a point, and we'll come up with this time and again. How this sinusoid looks depends on whether it is a sampled, or generated, right? In the analog world, you wouldn't sample anything. So any sinusoid that you create in the analog world, whether it's a sinusoidal signal that comes out from a AC generator, or it's a sinusoid that they create electronically using an oscillator of some sort, it is all the same. In the case of the discrete time domain, it is very different if the sinusoid is one. The sequence that we have on top here, for instance, if you forget this for the time being, just ignore that and just look at the dots. If you look at the dots, you really can't tell if that was created, mean generated, or if it was a continuous time signal that somebody sampled at those instances to give you that. And it makes a very important, we'll come to it in a short while, it makes a very important difference if it's generated or if it's sampled, okay? To do it, if you treat the signal as being periodic or not. But we'll just hold that for a little while. I just thought I'll introduce that at this point in time. Then below we have an exponential sequence. Again, the values, all you know in life, if you're given that, is these points here. By the way, these, just as an aside, these are created by something in MATLAB called a stem plot. Right? The actual values are the lollipop heads on the top there. The stems, which are the vertical lines, are just so that you can see where it lines up in the X domain, in this, which is supposed to be either the sample or time. Right? So this is not really part, the vertical line is not part of it at all. All you really supposed to see is this. Okay? And of course, okay, and then we have these two little things. You would have remember this from your Fourier series, but that's now dealing specifically with discrete signals. You have odd and even sequences. Now let's look at the even one. The even sequence is easy to manipulate, because if you flip it along that red line, it's symmetrical along the red line. Okay, so the even sequence xn is the same as x minus n. So you flip it around. In the case of the odd sequence now, it's two sets of things. You have to, if you flip it around here and then you flip it around here. Okay, so flip it around, you're going to get that, and then you flip it along so you flip it along the y axis and then the x axis, and then you eventually get the sequence. So that's why it's minus x minus n. Okay, so both of them have a strange symmetry about them. The even sequence, of course, is a mirror image. The odd sequence is like two mirror images in one. So it's reflected around both the y and the x axis. And we go down here now. So the beauty about this is that there are ways, a signal that is neither even nor odd, you can always break it up into a combination of an even and an odd sequence. And this is useful. One of the things you have to look at, let's go back here a little bit and just let me clear the annotations. If I know, let's look at the even sequence here. If I know that this sequence, that xn and x minus n is, that is the behavior between them, then what I do, if I have to do some sort of manipulation on this signal, then what I can do is just manipulate this part, which is half the values, And then whatever I do on this half, I just substitute that into the values that the values that I use here, right, on this side is just minus the indices, so I could save processing power. So just think if I have 500,000 values to process 250,000 values, and then the other 250 are the mirror image of the first 250. Yeah, same sort of thing here. So if I know a particular relationship, I could process this part of it, and then using the other half has a relationship to that, I could save a lot of processing time. So what happens is, now if you have a sequence that is neither odd, it's a very bad drawing here, so let me just clear that. If I had a sequence that was neither odd nor even, and I could break it up now into a combination of even and odds, then by doing that, I could basically reduce, even on that, reduce the work by at least half. And in the case of signal processing, because we're dealing with, we're processing numbers, so we're dealing with storage and we're dealing with memory, it is all, the less numbers you have to deal with, one, the less storage you have to consider, and of course, the faster the manipulation will work. And if you think about like electric vehicles, for instance, where you have signal processing controlling the motor operation, signal processing controlling the wheel rotations, processing controlling the steering wheel, the acceleration, the deceleration, the battery charging and discharging, and so on. The less information that the units have to do, of course, the faster, the less information that they have to process, the faster they will operate, the smaller they can be, and of course, the more money the manufacturers can save in the design, and of course, charge you more, make more profit. Right, periodic signals. So this is where one of the first sets of differences come about. In the case of the continuous time domain, a periodic signal only, it repeats itself after some, it repeats itself entirely after some time that we call the period. Okay, in the case of a discrete time signal like the one below, one of the things you have to distinguish is between the values, right, and the envelope. Okay, so what may happen is that a discrete time signal, for a discrete time signal to be periodic, remember it's a series of values, right? We'll get a better color than that. Remember, xn is, let's say, 5, 4, 3, 2, 1. For xn, sorry, xn is equal to that, 5, 4, 3, 2, 1. For xn to be periodic, it means after some interval, 5, 4, 3, 2, 1 has to be repeated again. 5, 4, 3, 2, 1. How long it takes for this 5 to reappear here and the sequence to complete itself is what is called a period, right? In other words, regardless of what the shape looks like, for a discrete time signal to be periodic, the entire sequence, the values, have to be repeated entirely. Now that gives us a little bit of an issue, that in the continuous time domain, that if I have a continuous time signal xt is continuous if I have, it repeats itself if I have some period that I add to it. So sine sine omega t plus capital T, it will repeat itself for any value of the frequency. It doesn't matter what if I have sine omega t, right? And I repeat it, let's say to sine omega t plus t, right? It doesn't matter what I do with this. That is periodic for all the values of omega or f. If you want to replace omega with 2 pi f, it doesn't matter. No matter what I do, what value of omega or f that I make or I choose, sine omega t will always repeat itself in whatever period I specify for it. That doesn't apply to the discrete time signals. Discrete time signals, the samples, the entire value, the value sequence that I have has to be repeated, okay? Regardless of what it looks like. You following? Make some sense? Let me just show you it here, for instance, right? So if I have a discrete time sinusoid, so cosine 2 pi nf, and we're going to get some more, what do you call it? We're going to have a lot more experience with this coming along. So if you're not following quite yet, when we start to talk about sampling, it will become a little more clear to you. But basically, if I have a discrete time signal xn, which is cosine 2 pi nf, f is the quote unquote the frequency for me, and n is the integer values. Remember, this only existing for n equal to 0, 1, 2, 3, 4, 5, etc. For this to be periodic, it means that there's some period where the entire set of values of xn will be repeated here. So in other words, if I were to just put the manipulation, of course phi is just a physical, ignore that for the time being. So cosine 2 pi nf, somewhere along the way, if it is periodic and the period is n samples, remember this is samples, and you run out of space here, but samples, right? So cosine nf, 2 pi nf, if this is periodic, it means that I must be able to find some number of samples where cosine 2 pi nf and cosine 2 pi nf plus 2 pi capital NF are the same. Now this can only work if this is an integer. In other words, a multiple of 2 pi. Remember, the cosine signal itself repeats itself every 2 pi. So this can only make sense if NF, that product right here, is an integer, meaning 1, 2, 3, 4, 5, etc. In other words, whatever is that frequency value f that I have has to be related to n, which is the period, and k, which is some integer, in this form. In other words, the frequency that I have for when I'm generating a sinusoid, the frequency that I pick has to be some rational number, so like 100 over 5,000. In other words, a ratio of 2 integers. We'll see where this comes about. This is the actual frequency in hertz, and this is what we call the sampling frequency here. Okay? It's not the same thing if you went back to the continuous time. It didn't matter if I had cosine omega t. I could pick omega for any value. I could have omega equal 100.5 radians per second. And then if I wanted to, and it will still be periodic with some period, and then I can change it to 121.73, and it will still be periodic. In the case of the discrete time signal, the frequency has to vary in a very particular way, in such a way that the period and the frequency are related by a whole number, an integer. Yeah? As I say, it's a little odd, but when you think about it, what you're trying to see is that this is a set of numbers. It is not, in the case of the sinusoid, the continuous time sinusoid, the envelope looks like that because all of the values are continuous. So when I'm saying that it's periodic, it means that this entire envelope repeats itself somewhere along the way. In the case of the discrete time signal, this is a set of values, 17321, right? If I'm saying that it's periodic, then it means after some set of samples, 12731 will repeat itself again. And that only happens under certain conditions. Yeah? Makes some sort of sense? Right? As I say, when we talk a little bit about sampling, you'll see where this will clarify, will become a little more clear. But there are some other slides that I'll show you in a second. Right? So one of the oddball things about a discrete time sinusoid is, for instance, if I have e to the j omega plus 2 pi n, right? So I have a sinusoid, e to the j omega naught n, right? Remember, n is the sample number, 0, 1, 2, 3, 4, 5, 6, 7, etc. If I, right, and you could say instead of that, you could also use something like cosine omega naught n, right? If you, because in the case of the discrete time sinusoid, if you look at it and I change omega 0 from omega 0 to omega 0 plus 2 pi, notice that as omega 0 increases, because 2 pi is, we're talking in, let's say, radians per second. Of course, you could see this as 2 pi f naught if you like. All right. If I go from 0, I could increase it up to 2 pi, and notice what happens. When I increase it, it comes back down to the same original frequency. This applies to any time I'm generating a sinusoid discretely. It doesn't apply to those when you sample a continuous time signal. But if I'm generating a sinusoid, which is what a number of applications do in discrete time, so like you're going to MATLAB and you tell it, generate the values for a sinusoid for me. You have to be careful that you would automatically assume that, like in the continuous time domain, I had cosine 2 pi ft. If I increase f, then f could go from 0, which is DC, up to any value that I want. In the case of the discrete time, if omega is 0, it starts off at one place. But if I keep increasing omega, so omega plus 0.1, 0.2, 0.3, all the way up, as soon as omega crosses the value of 2 pi, it flips back around to just omega 0 again. Right? Look at it. And you have to remember, just go back to the previous slide. Remember this omega 0 here is really this here 2 pi nf, right? And if you want to, so this is omega naught is 2 pi nf naught, which would really be 2 pi n k over n, right? So you can see already that I am picking the period here, and this is the numbers that I'm actually incrementing, 0, 1, 2, 3, 4, etc. Right? So let's look at what happens here. So not just expanded that. You remember E to the this is just what do you call it? This is pure mathematics here. I didn't do anything fancy. All I did is expanded this. So E to the because it's e to the j, I can just factorize the j and it will be e to the omega plus 2 pi. Yeah. You just open the brackets. That's all. So look at what happens here. So when omega is 0, that's DC. This is what the generated sequence looks like. I increase omega. So instead of omega now, I start at omega equal to 0, I have omega not equal to omega plus 0.1. So it starts to oscillate. I increase the value. Notice it's oscillating a little bit faster. And then when I reach pi, notice that the values now are alternating now. So this is as fast as it can go until at omega equal to pi. Notice that the values are going from -1 plus 1, -1 plus 1, all the way through. Right? So they're alternating now. So one sample is +1, one sample is -1. Right? So the frequency, let me just backtrack a little bit. So we started off at DC, then the values start to increase. Right, and this is the point that I was trying to indicate to you all. What you have to do mentally is to forget what this looks like. The envelope, ignore. You're not interested in the envelopes at all when you're dealing with a discrete time sinusoid. What you're interested in are the points. Forget all the envelopes. In your mind, your eye is telling you, okay, that's looking like a cosine. Fine. But we don't care about that. If you go on here now, you see it's not going to look, if you look at this thing, or you look at these two images here, this is not looking like any sinusoid or cosinusoid at this point in time. The values just going between positive and negative. Here, it's kind of still looking in a way. So mentally, it's looking like it's oscillating faster. But what's happening here now? Right? Or worse again, what's happening here? You're just going from positive to negative, positive to negative. All right? In your mind, yes, okay, this is now a higher frequency than this was. All right? And then if we keep increasing omega beyond pi, then it starts to go back the next way. And then eventually when we reach back to 2 pi again, it's back to DC. All right? So you just need to remember that for generating sinusoids, right? Only for generated sinusoids, that if you want to create, and we will come, I said, don't worry too much if it still is a little bit odd seeing this. When we talk about the relationship between this frequency, which is in the discrete time frequency, as compared to the continuous time frequency, which is f or the continuous omega, right? When we distinguish between the two of them, this will become a lot clearer to you. All right, but just remember the thing that in the case of a discrete time sinusoid, that as you increase the frequency, it increases to a maximum and then goes back down, because the whole thing is periodic. It starts at 0 and it will end back at 0 again. Okay? Fair enough? Some kind of clarity? Yeah, no, maybe? Right? So remember that. right? So in the continuous time domain, e to the j omega naught t, or if you like, cosine omega naught t is distinct for every distinct value of omega 0. In the case of the discrete time version, right, it is not unique for every time. And I'm using this now. This is the first time you're going to see that. We're going to start using capital omega to distinguish the frequencies in the discrete time domain from the lowercase omega in the continuous time domain. Okay? So it is not unique for in the discrete time domain. Whatever value we pick of capital omega is not unique for every choice, and it is periodic with a period of 2 pi. Okay? And just a little bit here, distinguish between the envelope of the signal and the actual signal value samples. In the case of the discrete time signal, the values have to repeat themselves after some period of time. If they don't, then the signal is not periodic. And we're going to have enough looking at that. Okay, I know it's just a first class and it's kind of odd. In the case of the continuous time domain, it doesn't matter. All the values exist for all the time. So once the period is encountered, then the entire envelope repeats itself. All right. So signal manipulation, one of the things is that we mentioned that discrete time signals, because they're stored as numbers, we could do a lot of manipulation that they can't do in the continuous time domain. So I'm going to show you a couple of slides now where the signals, one is a 200 hertz signal and one is a 400 hertz signal, and they are both sampled at 1,000 hertz, meaning that I looked at them and I took a value every 1,000 hertz. All right, so you're going to see now, here's the first one. The top one is a continuous time, so that is a 200 hertz signal. And if I sample it at 1,000 hertz, all right, it means that in every 200 hertz, in the 1,000 hertz, how many samples am I going to pick? You got to look at it right here. Right, if you look at the period, so one period here is running to that dotted line here. So in between a period, I'm taking 1, 2, 3, 4, 5 samples, and then I start back again. So the number of samples is the 1,000 divided by the 200, which is 5, right? So if I take a 200 hertz signal and divide it by 1,000 hertz, I am going to get 1,000 divided by 200, which is 5 samples. So the sampled signal looks like the one below. And again, if I were to ask you to ignore the envelope and just give you this, if I just give you this and don't tell you what it is, you really can't say if this was a sinusoid or not. Does it look periodic? Based on what we said before. Is it periodic? Yes, because the values are repeating, right? So you're seeing, yeah, 1, 2, 3, 4, 5. The values are repeating every 5 because we sampled it, yeah? Let's look at the other one. Here is a 400 hertz signal now, and I'm sampling it at 1,000 hertz. Now notice this one is a little bit odd because in the period here, I'm getting 3 things here. Oops, I'm getting 3 values here. Then the period ends. Look at the next value. When I sample it again, I get 3 values here. So in other words, if I were to do the same manipulation here, 1,000 divided by 400 is 2.5, 2.5. So clearly by sampling it this way, I'm not getting the same number of samples and watching at it. Does this look periodic? If I give you this, you would say, yes, it's looking periodic because the values repeat after 1, 2, 3, 4, 5, and then it comes back here. So this is telling me after 5 of these samples, it's repeating. But in reality, I know that it should repeat after this amount, this number. Yeah? So you see the little novel behavior that is happening inside of here. Let's look at these. Forget it. This scale, there's a little mistake on the diagram. This should be 2, 1, 0.50, right? Everything is scaled instead of multiplying by 2 there. But look at it. So the 200 hertz we just saw has 5 samples a cycle. The 400 hertz has either, well, depending on how you want to count it, it's really 2.5 per cycle, or it really has 5 every 2 cycles. Yeah. So question, what is the least number of cycles or samples, sorry, required to represent it? This is a big question, and we're going to answer that. And funnily enough, this is adequate. Right, the 400 hertz where we're getting like 2.5 samples, well, which we can't get, but really 2 or 3 samples per cycle is really suitable, right? But it's definitely not looking like a sinusoid at that point in time. But we will see that is not that we can actually, as far as signal processing is concerned, that is not too bad of an answer. Then we can do certain things. I have these 2 signals here, and I can add them. Sorry, in this case, I subtracted them. So here's a 200 hertz signal, and I take away the 400 hertz signal from it. So if I take these, so I take this one here, and I subtract, so this minus that. If I do that, then I get this one here, right? The analog signal looks something like that, right? That's a reconstruction. Now you could do, you could do signal manipulation. You could have a difference amplifier, and I could run the 2 of them and get the answer. We know how to do that with an op-amp, right? This is what it looks like on a continuous time domain. So the continuous time signal is looking like that, like the one on the bottom. The discrete time signal is looking like the one on this side here. What about multiplying them? It's not particularly easy. Yes, you can do it. There are op-amp circuits called multipliers. So I could take the 200 and multiply it by the 400. But in this case, I could do this mathematically. I could take 2 arrays. So I have the 200 hertz signal and the array of values for the 400 and the 200, and I can multiply them, right? A point-by-point multiplication. And I get the signal on the left-hand side here, right? If I were to reconstruct it, this is what it's going to look like. If I were to do it with an actual electronic circuit, this is what the actual voltage is going to look like, or I'm saying voltage, but this is what the actual signal is going to look like. This is what the discrete time version looks like, right? The sampled answer, right? So you see already that there are differences between the continuous time domain and the discrete time domain. Is this workable for us in practice? If this is what I really expected, and this is what I'm actually getting, can whatever I have work with the lower one? Right, this is where, well, this of course will be what the application will speak to, right? So for instance, the unit step, right? Here some signal. I'll come back to this slide in a little bit. So I could delay so I have a unit step here. I could advance it. Advancing means bringing it forward in time. And remember, we're talking about that in signals and systems, that stored information or discrete values, you can move them forward in time, or you could move them, you could delay them. You can't do that with a continuous time signal. And then I could flip it. So I could take this one and flip it around the axis, like when you're doing convolution, and you have the one at the bottom, right? And then I could invert the sequence, the unit step sequence. I could add two sequences together, so I get something like this, which is a pulse. Or I could take this now and multiply it by n, so I get something looking like this. Yeah? These are the kind of things that you have to do that the signal processing allows you to do. For instance, if you want to control a motor, many of you all, I think by now you would have controlled things like stepper motors for your microprocessor class. And how you do that, it would have been to generate a sequence of values that went to the motor, and a certain number of values that went to the motor, and it would move the motor, and then it would stop. This is how you generate these sort of waveforms. Think about trying to make a waveform like this in the continuous domain, right? It's very hard, or if not impossible, to do an arbitrary waveform like this. You wouldn't be able to. And then two last things before we end today. What you can do, one of the things that you could do if you're fairly sure of what the discrete time signal is doing, is to do something called upsampling and downsampling. Downsampling is where you discard a certain number of the values. So if the signal, like on the left-hand side, we have a number of values here, 20 values going between -10 and time interval -10 and +10. If I downsample it by 3 to 1, it means I discard every 2 samples, right? So I start with the first one, discard 2, take the third, discard 2, take the 6th, and so I keep going on. And I'm left with a much lower number. What this does is that it allows us, if this, for our purposes, is as good a representation of this takes a lot less space. Just think about it. If you have 1,000,000 values and you could downsample and get rid of half of them, the storage is a lot less. Okay? So you must be fairly sure this is called downsampling. And the reverse now is upsampling, where you take the sequence of values, right? And when you upsample, what you did is that you add a value in between these. So for instance, inside of here, I add 2 additional values in between here. Now the beauty about signal processing is that I could do some manipulation here. If I'm fairly certain that the sequence of values like this, in between, that they were behaving like that, what I could do is to ask the system to interpolate between these two and add 2 values between here. So in other words, I could upsample and insert values that would bring it back to look like this one here. If I'm not certain, what I could do is to interpolate zeros. So if I'm not too sure what was happening inside here, I could interpolate zeros in between here. This is called zero padding. And when we do the fast Fourier transform in a couple of weeks, you're going to see that this zero padding allows us to make this behave in the same way as this one. So zero padding allows us to make the signal like this behave almost as though it was the original sampled version here without losing information. It's an amazing conclusion, but we're going to see how that works. All right. So in reflection, we covered a number of new things today. Some of the things we know already, like how to delay, how to invert odd and even behavior. We know that. Some of the new things that we did today had to do with periodic signals. A continuous time signal, the periodicity of a continuous time signal is not dependent on the frequency of the signal. Once the signal is continuous and you change the frequency, the period it will always repeat itself periodically, right? A sinusoid or co-sinusoid will always repeat itself periodically because the period is always, if I have a signal f, the period is always 1 over f. In the case of a discrete time sinusoid or cosinusoid now, it is not so. The signal, for it to be periodic, all of the values have to be repeated identically. It doesn't matter what the envelope look like. The envelope could be looking sinusoidal, but the values are not repeating themselves. If the values are not repeating themselves, then it's not periodic. So specifically in the case of discrete time signals, there is a relationship between the digital frequency or the discrete frequency that you choose and the period. And that relationship, as we said, the relationship between the omega for the discrete time and the period has to be a rational number. In other words, a ratio of two integers. All right? So, and we will come to that specifically when we start to talk a little bit about sampling next week and manipulating some signals and so on. But there's a huge difference between continuous time and discrete time signals. That the question of what is periodic or not is totally different. One is continuous time sinusoids are periodic for all values of frequency. The discrete times are not, regardless of how it might look on the screen for you. Okay? So, any questions? I'm sure you have, but I mean, any immediate questions? You have to listen to this and read it up a little bit again, and then come back to me. But any immediate questions or concerns? Okay. It's not as bad as it sounds. It's just a little bit unusual, and it will make a lot of sense as we go forward very quickly. Okay. All right. So let me stop the recording here today.